Hello everyone! In this problem, we're given a number of different measurements that each have units with a unit prefix attached to them. So our units are not in meters, but in millimeters or nanometers. Not volts, but gigavolts. So each unit has some modifying prefix attached to it. This problem is asking us to take each of these measurements and rewrite them without the prefix on the unit, so that it is full length as a full decimal number. The trick with this problem is to understand how each unit prefix modifies the measurement, modifies the quantity of that measurement. Or perhaps more accurately, modifies the way that measurement is represented. Because all that a prefix really does is it changes where we're going to put the decimal point in the number. Or another way to think about it, and the way I like to think about it, is that each unit prefix could be thought of as representing a different power of 10. For example, let's start with part A, where the measurement we're given is 286.6 millimeters. And by the way, if you're new to this, there's no shame in looking at a table that explains what these unit prefixes are. Like, it's okay if you don't immediately know what the lowercase m means, or what the lowercase p means, or the n. If you're new to this and you're just figuring all this out, I don't think any teacher will expect you to memorize it all immediately. You'll probably have a table that you can use, or you can just look things up about what the prefixes mean. But over time, it will eventually be helpful to start memorizing them. Nonetheless, starting with part A, we have a unit that is 2 lowercase m's, and what the lowercase m means in the unit prefix position is milli. So if we have a unit that has a milli in front of it, then that basically represents 1,000th of that unit. So if we were to write out the number of its full length with the decimal point in its most accurate place, we would expect that decimal point to move somewhere to the left, because we would expect the way this number, this quantity, is represented to be something much smaller. Or the way I think is easiest to think about it is that this is just 286.6 meters multiplied by 10 to the power of negative 3. Because the milli prefix can be thought of as representing a power of 10 to the negative 3. So this is 286.6 times 10 to the power of negative 3 meters. I think doing this makes the problem pretty simple, because as long as you know which power of 10 corresponds to which unit prefix, then the real challenge of this problem is basically just knowing that you can convert from power of 10 notation to standard notation. And the idea there is that if the power of 10 is negative, then we move the decimal point to the left, and if the power of 10 is positive, then we move the decimal point to the right. And the number of spots that we move the decimal point will be the same as the number that is in that power of 10. So because our power of 10 is negative 3, then we're going to take the decimal point and move it 3 places to the left. This gives us a measurement where the decimal point is right to the left of the 2. So that is 0.2866 meters. And that is the answer to part A of the problem. That might be a little tricky to get hang of, especially since we do have a bunch of other unit prefixes to keep track of. So let's move on to part B, where we have 85 and then microvolts. So that little Greek mu symbol represents micro, which is a millionth of something. Or, using the power of 10 notation, having a micro there is the same thing as multiplying by 10 to the power of negative 6. So 85 microvolts is just 85 times 10 to the power of negative 6 volts. The decimal point is, of course, right to the right of the 5. So to write this number out in its full notation, we're going to take the decimal point and move it 6 spaces to the left. Once we do that, we find that this is equal to and then 4 zeros, 1, 2, 3, 4, 8, 5 volts. Moving on to part C, we have 760 mg. Just like in part A, that lowercase m just means milli or a thousandth, so we can expect that our answer is going to be something that looks smaller. And so, just like in part A, we can think of this as a power of 10 to the negative third power. So that's 760 to the power of negative 3 grams over the 10. So taking the decimal point, which is to the right of the 0, and moving it over 2, 3 spots to the left, then we can see that this is equal to 0.760 grams. Now, as a quick aside, there is something a little odd, or a little interesting, I should say, about part C of the problem, and it's something that even the official solution to this problem kind of makes note of. Because with mass, which is what gram is a unit of, mass units are kind of unusual in typical physics problems, because it's considered standard for measurements of mass to be written as kilograms, rather than just plain grams. Even in ordinary, common, low-level physics problems, it's actually very rare that you'll see something measured in just grams. You'll usually see the unit prefix there, which is kind of unusual for even basic physics problems. And it's something worth considering with mass. So the official solution to this problem kind of suggests that there's a chance that your teacher might actually expect you to write this in kilograms rather than grams. Even though, strictly speaking, that's not even what the problem's actually asking for. But just so that I've got my bases covered, I'm going to quickly show how to do that. And this is where things can get really tricky and really confusing, because we're now adding a unit rather than taking the unit. We're adding a unit prefix instead of taking the prefixes away like we've been doing, which kind of turns the entire process up on its head. So I'm going to use a different color here to show this is kind of a side thing that might not be important to the problem itself. But our goal now is to add a unit prefix of k. And like I said earlier, I like to think of the unit prefixes as representing different powers of 10. And the k, the thousand prefix, represents a power of 10 to the power of positive 3. Note that it's kind of the opposite of the lowercase m, or milli prefix, because the milli prefix represents a power of 10 to the negative 3, the k represents a power of 10 to the positive 3. This is because the k represents a different modification to the order of magnitude of the quantity, whereas milli is 1,000th of something, much smaller than that something. K is 1,000 of that something, so it's much more of that thing. They modify the decimal point in opposite directions. However, because we're trying to add a unit prefix to a number that currently doesn't have one, the 0.760 grams, our method is going to be kind of reversed. So I'm going to add the power of 10 to the number, 0.760 times 10 to the power of, but instead of writing a positive 3, instead I'm going to put a negative 3, because the fact that we're adding the unit means that we're doing our previous process in reverse. So it's 10 to the power of negative 3 to get the kilograms there. So once again, we're going to be taking this decimal point and moving it 3 spots to the left to make our quantity look even smaller. So our result will be 0.00076 kilograms. And so that is the answer to part C, or at least it's another way of writing the answer to part C. I think that our first answer up here technically answers the problem better, the way the problem is phrased, but for some reason the official solution uses this solution. And I guess it makes sense, because again, mass is much more commonly written as kilograms, but it is a little confusing. Fortunately, the rest of the parts of this problem are pretty straightforward, much more straightforward than that one. Part D, we've got 62.1 picoseconds. So that's 62.1, and we're going to use a power of 10, and the pico unit prefix represents a power of 10 to the negative 12. So that's 62.1 times 10 to the power of negative 12 seconds. So we're going to take this decimal point and move it 12 spaces to the left. This is the same thing as a decimal point followed by, so we're moving this decimal point 12 spaces to the left. So we're going to be covering the 6 and the 2, and then 10 more spots. So this is going to be equal to 0 point, and then 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 6, 2. 1 seconds. And that is the answer to part D. In part E, our number is 22.5 nanometers. Now the nano unit prefix represents a power of 10 to the power of negative 9. So it's 10 to the power of negative 9 meters, which means we're going to take the decimal point and move it over 9 spaces to the left. Doing this, we get a result of 0 point and then 7 zeros. 1, 2, 3, 4, 5, 6, 7, followed by 2, 2, 5. And then we put the meters. And that is the expanded form for part E. Part F, the unit is 2.50 gigavolts. I don't know why the problem is written in a way so that giga is written out instead of using the typical abbreviation. Usually, giga as a unit prefix is abbreviated as a capital G, but it's written out and that's fine for us. It doesn't change anything. It's just noticeably inconsistent, but whatever. Anyway, this part of the problem is still fairly simple, because we're going to use the same idea as before. What power of 10 does giga represent? Well, it represents 10 to the power of 9. Yeah, not 10 to the power of negative 9, like in part E, but 10 to the power of positive 9. So this is going to give us a result. This is going to give us a quantity that looks much larger than the one we're starting with. So we're actually going to take this decimal point and move it over 9 spaces to the right. So we're going to have a result that looks like a larger number. And once we move the decimal point 9 spaces to the right, we find that the result is 2.5 billion volts. So that's 2,500,000,000 volts. And that is the number written out all the way. And that is now it for every part of this problem. So yeah, kind of confusing at some points. There are definitely some weird nuances in here to keep in mind. But for the most part, you take the unit prefix, figure out which power of 10 it corresponds to, and then convert it from a power of 10 to a full number by moving the decimal point to the left or to the right by that number of spaces. And that is it for this problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos like this. If you have a request or a question, leave a comment down below, and I'll do my best to help you out as best I can. That's all for now, and I hope you all have a lovely day. Bye-bye.